Today we're going to learn about an organic compound called thymoquinone. We learned the common name, now we're going to learn the IUPAC nomenclature. 2-isopropyl 5-methyl-1,4-benzoquinone. This organic compound is a bioactive constituent of Nigella sativa. The chemical formula of thymoquinone is C10H12O2. The molecular weight is 164.204 grams per mole, and it has a melting point of 49 to 50 degrees Celsius, and it has a boiling point of 230 to 232 degrees Celsius. Thymoquinone is a solid bright yellow compound. It has scaly crystals and an intense smell of pepper. In all aqueous solutions, solubility varies from 549 to 669. This is because it is unstable in all aqueous solutions, specifically in alkaline pH. That's why it varies so much. And it also has a severe light sensitivity, and you'll notice this when you buy it at the grocery store, that it comes in dark, opaque bottles. Thymoquinone is known to show keto-enol tautomerism. In the picture, we see the enol form and the keto form. We learned that the keto form makes up about 90%, while the enol form makes up about 10%. This means that the keto form is the major configuration. Thymoquinone is able to do this because it's a tautomeric compound. This means two or more chemical compounds are able to change between each other because they exchange a hydrogen atom and they form a covalent bond. It's different from other types of isomers because tautomeric compounds exist in mobile equilibrium, which means if you're trying to separate two substances, it usually ends up with a combination and a mixture of the two compounds. Focusing our attention to the middle of the compound, we can see that the enol form has a sigma bond attached to a hydroxyl group, while the bottom, the keto form, has a pi bond attached to an oxygen. This furthers the benefits of thymoquinone because the keto form is what gives it its pharmacological uses. However, thymoquinone is hydrophobic, which means it has problems with solubility and therefore its bioavailability is limited. So that means that if we ingest it, it can have trouble actually being absorbed in the body. Research studies have found that thymoquinone is known to increase the activity and number of cytokine suppressors, lymphocytes, natural killer cells, and macrophages. This means that it helps our immune system fight against colds and bacteria. Another factor that makes this compound unique is its antioxidant effect. This is due to its high radical scavenging capabilities. In our day-to-day lives, we perform cellular respiration. This causes the formation of reactive oxygen species. Now, thymoquinone counteracts this by activating the enzymes that protect cells from cellular damage caused by that oxidative stress. This is important because oxidative stress can cause a multitude of problems such as diabetes, inflammation, cardiovascular disease, and cancer. Several studies have even shown that thymoquinone does this by increasing the expression of mRNA and stimulating various cytoprotective antioxidant enzymes. In this picture, we can see dithymoquinone and thymohydroquinone. These are the two most frequently synthesized close derivatives of thymoquinone. A major difference I noticed between thymoquinone and dithymoquinone is that it looks like it's connected by cyclobutane in the middle. In thymohydroquinone, I noticed that the ring is fully conjugated, and instead of pi bonds connected to an oxygen, it's a sigma bond connected to a hydroxyl group. This diagram shows the biosynthesis of thymoquinone. Here we see that geranyl diphosphate undergoes cyclization and forms Y-terpinene. This means, by definition, and also the picture shows, that it is the formation of a ring. It is then aromatized into p-cymene, which means it becomes a fully conjugated ring. This is then followed by hydroxylation to carvacrol. It goes through another round of hydroxylation and forms thymohydroquinone. It will then undergo oxidation and lead to the end result of thymoquinone. If we were to use these compounds in laboratory, these would be the results we would get for HNMR and CNMR. In the first picture, we have HNMR, and it shows that there are 4 distinct proton environments. This drawing allows us to see where those unique proton environments come from. We have a septet, a singlet, a quadruplet, and a doublet. CNMR allows us to understand the outline of the carbon skeleton. In this graph, we can see that there are 10 signals. Therefore, we understand that there are 10 carbon atoms in this compound. I chose this compound because I became really interested in hair care, and there's a really big trend now on oiling your scalp. And this was one of the compounds that they said is really good for hair retention and for hair growth. However, the articles that I read were more concerned on its anti-inflammatory, antioxidant properties, which is also something that really piqued my interest. So in my intended career, this is a chemical that I think would be really helpful because it's a more holistic approach to healing the body.